The idea of nothing has profoundly challenged human thought for thousands of years. When people first began asking questions about existence, they quickly encountered a strange and unsettling problem. What does it mean for something to not exist at all? In everyday life, people use the word nothing quite casually. Someone might say there is nothing in a box, meaning the box is empty. But even in that simple example, the box itself still exists, the air inside still exists, and the space is still there. So that nothing is not absolute. It is simply a way of saying that a particular expected object is absent. Philosophers have noticed this problem and have raised a more serious question. Is an absolute nothing even possible? One where there is no space, no time, no matter, no energy, and not even the possibility of something? One of the first thinkers to confront this question was the ancient Greek philosopher Parmenides. He argued that what is not cannot exist in any form. According to him, thinking about nothing is impossible, because by thinking about something, even if it is nothing, one already grants it some form of existence in the mind. In his view, only being is real, and non-being cannot be. This idea may seem strange, but it forced later thinkers to face a serious problem. If nothing cannot exist, how do we explain change, absence, or disappearance? Later, philosophers began to explore this problem from different angles. Some attempted to accept that nothing might exist in some limited sense, while others insisted it is merely a concept created by language. The Greek philosopher Aristotle took a more practical approach. He rejected the idea of a true void, that is, a space completely empty of everything. He believed that nature does not allow such a vacuum, and that what people call empty space is still something that exists in its own way. As philosophical thought spread beyond ancient Greece, different cultures developed their own ideas about nothing. In parts of Asia, especially in traditions influenced by Buddhist thought, the idea of emptiness became central to understanding reality. In this context, emptiness did not mean a total absence of everything. Instead, it pointed to the idea that things have no fixed, independent essence. Everything depends on other things to exist, and nothing exists entirely on its own. This view shifts the meaning of nothing from a total absence toward a deeper understanding of how existence itself works. In this way of thinking, nothing is not something to be feared or avoided. It is not a dark void that threatens existence. Instead, it is a way of seeing that what people consider solid and permanent is actually fluid and interconnected. A person, for example, is not a fixed object, but a collection of changing processes, relationships, and conditions. When these conditions change, the person changes. From this perspective, nothing becomes a way of understanding that there is no permanent core behind things. Moving forward in history, European philosophers began to reconsider the idea of nothing with renewed intensity. During the period known as the Enlightenment, thinkers focused heavily on reason and logic. They attempted to build systems of thought that explained the world in a clear and structured way. However, even within these systems, the idea of nothing remained difficult to handle. It did not fit easily into logical categories, because it seemed to lie outside the very boundaries of existence. One philosopher who took this challenge seriously was Immanuel Kant. He argued that the human mind has limits and that some questions may be impossible to answer completely. According to him, the idea of nothing is one of those difficult areas where the mind attempts to go beyond its natural boundaries. When people try to imagine absolute nothing, they often end up imagining something like empty space or darkness. But that is still a form of existence. For Kant, this showed that the human mind cannot truly grasp complete nothingness. In the 19th century, the discussion about nothing took a more intense and personal turn. Philosophers began to connect the idea of nothing with human experience, especially with feelings of emptiness, meaninglessness, and uncertainty. One of the key figures in this shift was the Danish philosopher Søren Kierkegaard. He explored how individuals face the possibility that life has no clear or guaranteed meaning. In this context, nothing became linked to anxiety. It was not merely a concept, but a feeling that arises when people realize their choices are not determined by any fixed structure. This idea was developed further in the work of later philosophers, especially those associated with existentialism. These thinkers placed human existence at the center of their philosophy. They argued that people are not born with a fixed purpose, but must create meaning through their actions. This freedom can be empowering, but also unsettling. When there is no given meaning, the possibility of nothing always exists, a kind of void where purpose might disappear. The philosopher Jean-Paul Sartre explored this idea in detail. He argued that nothing is not merely an abstract concept, but something that appears within human consciousness. For example, when a person expects to meet a friend at a certain place, and the friend does not arrive, the absence becomes noticeable. The person experiences a kind of nothing in that moment. According to Sartre, this ability to recognize absence shows that nothing is connected to human consciousness. Sartre went further to suggest that nothing plays a role in freedom. Since people are not fixed objects, they can always distance themselves from their current situation and imagine different possibilities. That space between what is and what could be creates a realm in which nothing exists. It is not a physical void, but a kind of openness that allows for change and choice. Another philosopher, Martin Heidegger, approached the question of nothing in a different but related way. He argued that human beings have a unique relationship with existence because they are aware of it. This awareness includes the recognition that existence can end. For Heidegger, the experience of anxiety reveals the presence of nothing. In moments of deep unease, the familiar world can lose its meaning, and a person may feel that everything is slipping away. In such moments, nothing is not just an idea. It is something that shapes the way reality is experienced. Heidegger believed that confronting this kind of nothing can lead to a more authentic way of life. When people recognize that their existence is not guaranteed and that it will eventually end, they can begin to take their choices more seriously. In this sense, nothing becomes a way of understanding the limits of life and the importance of individual responsibility. Although these philosophical ideas may seem abstract, they often connect closely with everyday human experiences. Feelings of emptiness, loss, or uncertainty can bring the idea of nothing into personal life. For example, when someone loses a loved one, a sense of absence arises that can feel overwhelming. The person who was once present is no longer there, and this absence can influence the way the world is perceived. Philosophers have used these kinds of experiences to explore how nothing is not just a theoretical concept, but something people encounter in real situations. At the same time, some thinkers have attempted to approach nothing in a more logical and analytical way. They ask whether it is possible to define nothing in clear terms. This often leads to difficult questions. If nothing is truly nothing, then it cannot have properties. It cannot be described, measured, or even thought about without turning it into something. This creates a paradox. The moment people try to describe nothing, they seem to give it some form of existence. Language plays an important role in this problem. Words are designed to refer to things, actions, or ideas. When people use the word nothing, it seems to function as a name, as if referring to something specific. But if nothing is not a thing, then the word may be misleading. Some philosophers argue that many of the problems surrounding nothing arise from the way language is structured. They suggest that by examining how words are used, it may be possible to avoid the confusion. In more recent times, philosophers have continued to explore the idea of nothing in new ways. Some have connected it to questions about reality itself. They ask whether the existence of something rather than nothing requires an explanation. Why does the universe exist? Why is there not simply nothing? This question has no easy answer and remains one of the deepest mysteries in philosophy. Others have approached nothing from the perspective of human identity. They ask what it means for a person to exist, and whether there is a stable core that defines who someone is. If a person changes over time, losing memories, gaining new experiences, and shifting their beliefs, then what remains constant? Some philosophers suggest that there may be no fixed essence at all. From this point of view, the self is not a solid object, but a process. And the idea of nothing helps to reveal this fluid nature. There are also debates about nothing in relation to death. Many philosophical traditions have tried to understand what happens when life ends. Some argue that death is a return to nothing, a complete absence of experience. Others contend that this state is impossible to imagine, because any attempt to imagine it involves some form of consciousness. This leads to ongoing debates about whether death can truly be understood. In addition to these serious and sometimes heavy themes, the idea of nothing has also inspired creativity. Writers, artists, and thinkers have used it as a subject to explore the limits of imagination. In trying to describe nothing, they often reveal the limits of thought itself. This can give rise to new ways of seeing the world and questioning assumptions that are normally taken for granted. Despite all these efforts, the idea of nothing remains difficult to fully grasp. It sits at the edge of understanding, where language, logic, and imagination begin to break down. Each philosophical approach offers a different way of thinking about it, but none provides a final answer that resolves all the questions. Some thinkers accept this uncertainty and see it as part of the value of philosophy. Rather than trying to eliminate the mystery, they explore it, using it as a way to deepen understanding. In this sense, nothing is not merely a problem to be solved, but a doorway into new ways of thinking about existence, meaning, and reality. When scientists talk about empty space, they do not mean a place that contains absolutely nothing. In everyday language, people tend to imagine empty space as a total absence of everything, a kind of absolute blank where there is no matter, no energy, and no activity. However, in science, especially in fields such as physics and astronomy, the idea of empty space is far more complex and less straightforward. What scientists call a vacuum is not truly empty. It is a state in which the amount of matter is extremely low, but one that still contains energy, fields, and constant activity that cannot be seen directly by the human eye. To understand this idea clearly, it helps to start with how people initially thought about absence. For a long time in history, many thinkers believed that a true vacuum could not exist at all. They thought that nature would always fill any empty region with something, whether air, water, or another type of substance. Later, scientists began to test these ideas through experiments. They created devices capable of removing air from a container, forming what they called a vacuum. These early experiments showed that it was possible to reduce the amount of matter in a space. But even so, the space was not completely empty. In modern science, a vacuum is defined as a region in which the number of particles is very low compared to normal conditions, such as those at the surface of the Earth. For example, the air around people contains many molecules, such as oxygen and nitrogen. In a vacuum, most of these molecules are removed. However, even the best vacuum created in a laboratory still contains some particles. These may be very few, but they are still present. Scientists measure how empty a space is by counting how many particles exist within a given volume. A high-quality vacuum may contain only a few hundred particles in a space where normal air would hold billions and trillions. Even so, it is not completely empty. The idea of a perfect absence, in which there are absolutely no particles whatsoever, is something scientists have neither been able to create nor observe. When scientists study outer space, they also describe it as a vacuum. The space between stars and galaxies contains far fewer particles than any vacuum that can be created on Earth. Yet even this vast space is not empty. It contains small amounts of gas, dust, and other particles. Forms of energy are also present, such as light from distant stars and radiation from various sources. Another important part of understanding empty space is the concept of fields. In physics, a field is something that exists throughout space and can influence objects. For example, there are gravitational fields and electromagnetic fields. These fields are present even in regions where there are no visible particles. This means that even if all matter were removed from a region, these fields would still exist. One of the most important fields in modern physics is the electromagnetic field. It is responsible for light, radio waves, and many other forms of energy. This field exists everywhere, even in a vacuum. When scientists describe a region as empty, they do not mean that this field has disappeared. Instead, they mean that there are very few particles moving through it. Another key idea comes from quantum physics, which studies very small particles and the fundamental nature of reality. In quantum physics, empty space is neither silent nor static. It is filled with activity at a very small scale. Even when there are no particles present in the usual sense, the vacuum contains what scientists call quantum fluctuations. These are temporary changes in energy that occur spontaneously. Quantum fluctuations mean that particles can appear and disappear over very brief periods. These particles are often called virtual particles. They are not observed directly like ordinary particles, but their effects can be measured. This shows that even what appears to be empty space is constantly active. The idea that empty space has energy is also very important. Scientists call it vacuum energy. It is the energy that exists in space even when there are no particles present. This energy is linked to the behavior of quantum fields. It cannot be removed and is always present. Some scientists believe this energy plays a role in the expansion of the universe. When scientists talk about the expansion of the universe, they are describing how space itself increases over time. Galaxies are moving away from one another, and the distance between them grows. This expansion does not happen because galaxies are moving through empty space like objects traveling through air. Instead, it is space itself that is stretching. This means that empty space is not just a passive background. It has properties that can change and influence the behavior of the universe. Another way to understand empty space is to observe how light travels through it. Light can move through a vacuum without needing a medium such as air or water. This shows that space allows energy to pass through it. However, the presence of fields and quantum effects means that light does not travel through absolute nothingness. It moves through a region that has structure, even if that structure is not visible. Scientists also study how particles behave in a vacuum. In experiments, particles can move freely without being slowed by air or other materials. This allows researchers to study their natural behavior more clearly. However, even in these experiments, the vacuum still contains fields and small amounts of energy that can affect the results. In outer space, the idea of empty space becomes even more interesting. The regions between stars are extremely empty compared to conditions on Earth, yet they still contain particles, such as atoms of hydrogen and helium. Cosmic rays also exist. These are high-energy particles that travel through space. These particles can cover great distances without interacting with anything. Space also contains radiation from many sources. Stars emit light and other forms of energy. There is also background radiation that comes from the earliest stages of the universe. This radiation fills all of space and can be detected with sensitive instruments. This means that even the most empty regions of space are filled with energy. Another important aspect of empty space is gravity. Gravity is not something that requires matter to exist. It is a property of space and time. Massive objects such as planets and stars generate gravitational effects that extend throughout space. Even in regions far from any object, gravity can still have influence. Scientists describe gravity through the idea of space-time. Space-time combines space and time into a single concept. According to this idea, massive objects cause space-time to curve. This curvature affects the way objects move. Even in regions that appear empty, space-time still exists and can be shaped by distant objects. This shows that empty space is not simply a blank zone. It has structure and properties that can influence the behavior of matter and energy. It is part of the overall system that makes up the universe. Another concept related to empty space is dark energy. This is a form of energy that scientists believe exists throughout all of space and is responsible for the accelerating expansion of the universe. Dark energy is not observed directly, but its effects can be measured through the movement of galaxies. This suggests that even empty space may contain forms of energy that are not yet fully understood. Scientists also study how empty space behaves under different conditions. For example, in very strong gravitational fields, such as those near black holes, the properties of space can change in extreme ways. Time can pass differently, and the behavior of particles can be affected. This shows that empty space is not always the same everywhere. Its properties can vary depending on the surrounding environment. In laboratories, scientists attempt to create conditions as close as possible to a perfect vacuum. They use special equipment to remove air and other particles. These experiments are important for studying fundamental physics. However, no matter how advanced the equipment, it is not possible to completely eliminate all particles and energy. Even if all particles could be removed, quantum fields and vacuum energy would still be present. This means that a truly empty space, in the sense of containing absolutely nothing, may not exist in reality. Instead, empty space is always filled with some level of activity and energy. The idea of empty space also plays a role in technology. For example, vacuum conditions are used in devices such as electron microscopes and particle accelerators. These instruments require a low number of particles so that electrons or other particles can move without interference. This allows scientists to study very small structures and high-energy processes. In space exploration, understanding the nature of empty space is important for designing spacecraft and instruments. Spacecraft must be able to function in a vacuum, where there is no air to carry away heat or provide resistance. Engineers must consider how materials behave under these conditions. Another interesting point is how humans perceive empty space. To the human senses, a vacuum feels empty because there is no air to see or feel. However, this perception is limited. Scientific instruments can detect particles, fields, and radiation that are not visible. This shows that what seems empty to the human senses is not truly empty when studied in detail. Researchers are also exploring how empty space behaves at very small scales. At these scales, the effects of quantum physics become very important. Space may not be smooth and continuous, but could instead have a structure that changes at extremely small distances. This idea is still being investigated and is not yet fully understood. The concept of empty space also raises questions about the nature of reality. If space is never truly empty, then it suggests that the universe is always filled with something, even in places where there is no matter. This challenges simple ideas about emptiness and encourages deeper investigation. Scientists use mathematical models to describe empty space and its properties. These models help them predict how particles and energy behave. They also help in understanding phenomena, such as the expansion of the universe and the behavior of black holes. Observations from telescopes and experiments provide data that support these models. For example, measurements of the cosmic background radiation and the movement of galaxies offer information about the energy present in space. These observations show that empty space has measurable effects. Another area of research involves the possibility of using vacuum energy for practical purposes. Some scientists have suggested that it might be possible to extract energy from empty space. However, this idea remains theoretical and has not been achieved in practice. When people first hear the expression "the void of space," they often imagine a place that contains absolutely nothing. A completely empty, silent, and motionless place. It may seem like a vast region where there is no matter, no light, no movement, and no activity of any kind. However, scientific understanding has gradually shown that this idea is not correct. What appears to be empty space is actually filled with subtle forms of energy, tiny particles, and different types of radiation that are always present, even in the darkest and most distant regions of the universe. To understand this idea, it is important to begin with how scientists define a vacuum. In everyday language, a vacuum is usually described as a space without air. On Earth, this can be created inside sealed containers, where air is removed using special machines. These artificial vacuums are used in laboratories and industries and can reach very low pressure levels, meaning that very few air molecules remain inside. However, even in these carefully controlled environments, it is nearly impossible to remove every single particle. There are always some atoms or molecules left, moving slowly and rarely interacting with anything else. When scientists talk about the void of space, they are referring to a natural environment that exists beyond the atmospheres of planets. Space does not contain air like the Earth does, so it is often described as a vacuum. But this vacuum is not perfectly empty. It is actually an environment of extremely low density, meaning that particles are spread very far apart across great distances. In some regions of space, there may be only a few atoms in a volume that on Earth would contain billions of atoms. This makes space seem empty, but it is not completely so. One of the simplest things present in the void of space is matter in the form of individual atoms and molecules. These are mostly hydrogen atoms, since hydrogen is the most abundant element in the universe. There is also helium, along with traces of other elements. These atoms float through space, sometimes gathering into clouds, known as interstellar clouds. In some cases, these clouds can become dense enough to form new stars over long periods of time. Even in regions where matter is very scarce, particles still exist and move slowly through the void. In addition to atoms and molecules, space also contains smaller particles such as electrons and protons. These particles can move freely through space and are often influenced by magnetic and electric fields. Many of them come from stars, including the Sun, which constantly releases a stream of charged particles known as the solar wind. This flow of particles travels through the solar system and interacts with planets, moons, and other objects. Even far from stars, particles continue to exist and travel through the void over great distances. Another important feature of space is radiation. In this context, radiation refers to energy that travels through space in the form of waves or particles. One of the most familiar types is visible light, which allows humans to see stars and galaxies. However, visible light is only a small part of a much broader range called the electromagnetic spectrum. This spectrum includes radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. All of these forms of radiation travel through space, even in regions that appear completely dark to the human eye. The presence of radiation means that space is constantly active, even in places where there are no nearby stars. For example, there is a form of radiation called the cosmic microwave background radiation. This radiation is found throughout the entire universe and is considered a remnant from an early stage in the history of the universe. It fills all of space and provides evidence that the void is not empty, but contains energy that has existed for an enormously long time. The energy in the void of space is not limited to radiation alone. Modern physics has introduced the idea that even empty space itself has energy. This concept comes from the study of quantum physics, which examines how particles behave at very small scales. According to this field, space is never completely still or empty. Instead, it is filled with small fluctuations that occur on a constant basis. These fluctuations can briefly create pairs of particles that appear and disappear within extremely short intervals. These temporary particles are known as virtual particles, and their existence suggests that the void is a dynamic environment. The idea that empty space contains energy is supported by various observations and experiments. One example is a phenomenon known as the Casimir effect. This effect occurs when two very thin metal plates are placed extremely close together in a vacuum. Scientists have observed that the plates experience a small force pushing them toward each other, even when there is no obvious source of that force. This behavior is explained by the presence of quantum fluctuations in the vacuum, which generate differences in energy between the space inside and outside the plates. Another important aspect of the void of space is the presence of gravitational fields. Gravity is not limited to planets and stars. It extends throughout all of space and affects everything within it. Even in regions far from massive objects, gravitational influence is still present, though it may be very weak. These gravitational fields can affect the movement of particles and radiation, shaping the structure of the universe over time. Dark matter is another component that plays a role in the nature of space. Although it cannot be seen directly, scientists believe that dark matter makes up a large portion of the total matter in the universe. It does not emit or absorb light, but its presence can be detected through its gravitational effects on visible matter. Dark matter exists throughout space, even in regions that would otherwise appear empty. Its influence helps hold galaxies together and affects the movement of objects within them. In addition to dark matter, there is also a form of energy known as dark energy. This energy is believed to be responsible for the expansion of the universe. Observations have shown that galaxies are moving away from one another, and this movement is accelerating over time. Dark energy is thought to be a property of space itself, meaning that even empty space contains this form of energy. As the universe expands, more space is created, and with it, more dark energy. The void of space is also affected by events that occur in different parts of the universe. Explosions such as supernovas release enormous amounts of energy and particles into space. These materials travel across vast distances, contributing to the overall content of the void. Similarly, the activity of black holes can influence their surroundings through the emission of radiation and jets of particles. These processes ensure that space is constantly being filled with new forms of matter and energy. Temperature is another factor that demonstrates that space is not completely empty. Although space is often described as very cold, it still has a measurable temperature. This temperature is influenced by the radiation present in space, including the cosmic microwave background radiation. Even in the coldest regions, some level of thermal energy still exists. Magnetic fields also exist in space and play a role in how particles behave. These fields can extend over great distances and influence the movement of charged particles such as electrons and protons. Magnetic fields are generated by stars, planets, and other celestial objects and continue to exist even in regions where matter is scarce. The study of the void of space has led to a deeper understanding of the universe and its fundamental nature. Scientists use advanced instruments to detect the faint signals that exist in space, including small amounts of radiation and the presence of distant particles. Telescopes that observe different parts of the electromagnetic spectrum allow the study of regions invisible to the human eye. These observations reveal that space is far from empty and is instead filled with activity at many different levels. Spacecraft traveling beyond the Earth also provide valuable information about the void. Instruments on board these spacecraft measure particle density, the strength of magnetic fields, and the intensity of radiation in different regions. These measurements help scientists build a more complete picture of what space is like and how it behaves. The idea that space is not empty has important implications for many areas of science. It affects the way scientists understand the formation of stars and galaxies, the behavior of particles, and the evolution of the universe. It also influences practical considerations for space travel, as spacecraft must be designed to withstand radiation and interaction with particles. The void of space, when examined closely, reveals a complex environment containing a variety of elements and forces. At first glance, it may appear to be an immense nothingness, but careful study shows that it is filled with subtle and constant activity. Tiny particles pass through it. Energy moves in multiple forms, and even the structure of space itself shows signs of movement and change at very small scales. Long before modern science began to explore the smallest parts of reality, the idea of nothing seemed clear and straightforward. It suggested a complete absence, a state in which there is no matter, no energy, no movement, and no activity of any kind. It seems simple because in everyday life, empty space appears to contain nothing at all. An empty room, an empty box, or the space between objects all seem silent and inactive. However, when scientists began to study the nature of space at very small scales, this familiar idea began to break down in unexpected and difficult to imagine ways. The development of quantum mechanics changed the way scientists understand reality at its deepest level. This field of study focuses on the behavior of particles too small to be observed directly, including atoms and the even smaller parts that make them up. At this scale, the rules that govern movement, energy, and existence are not the same as those that apply to everyday objects. Instead of stable and predictable behavior, there is uncertainty, constant change, and a level of activity that continues even in places that appear completely empty. At the center of this new understanding is the idea that empty space, often called the vacuum, is not truly empty. In classical physics, a vacuum was defined as a region containing no particles. Scientists could create something close to this in a laboratory by removing air and other substances from a sealed container. These conditions produce what is known as a near-perfect vacuum. Even so, small traces of matter or energy always remain. More importantly, quantum mechanics shows that even if all particles were completely removed, something would still exist. This conclusion comes from one of the most important ideas in modern physics, known as the Heisenberg uncertainty principle. This principle states that certain pairs of properties, such as position and movement, cannot both be known with complete accuracy at the same time. This is not due to limitations of measuring instruments, but because nature itself does not allow these values to be completely defined simultaneously. Uncertainty is built into the very structure of reality. Because of this principle, the energy in a vacuum cannot remain perfectly at rest or be exactly equal to zero. If the energy were exactly zero, it would mean that both its value and its rate of change are known with total precision, which would violate the uncertainty principle. As a result, even in a region where no particles exist, energy must still be present in an unstable and changing form. This gives rise to what scientists call quantum fluctuations. Quantum fluctuations are small, temporary changes in energy that occur everywhere, even in empty space. They are not rare events, but constant features of the vacuum. These fluctuations happen so quickly and at such small scales that they are not perceived in everyday life. However, their effects can be measured in experiments and have real consequences in the physical world. One of the most striking results of quantum fluctuations is the appearance of what are known as virtual particles. These are short-lived particles that seem to arise from empty space and disappear again within extremely brief periods. They are called virtual because they cannot be observed directly like ordinary particles, but their presence can be detected through the influence they have on other systems. Virtual particles do not behave like stable matter. They arise in pairs, often as a particle and its opposite, known as an antiparticle. These pairs quickly come together and annihilate each other, returning their energy to the vacuum. This process occurs continuously and throughout all of space. This means that what appears to be nothing is, in reality, a place of constant activity at a very deep level. The idea that particles can appear and disappear may seem strange, but it follows the rules of quantum mechanics. The energy needed to create these particles is borrowed from the vacuum for a very short time. As long as the particles disappear quickly enough, the total energy remains consistent with the uncertainty principle. This constant borrowing and returning of energy forms part of the active nature of the vacuum. Scientists have found ways to detect the effects of these virtual particles. A well-known example is the Casimir effect, in which two very closely spaced metal plates in a vacuum experience a small force pushing them toward each other. This force cannot be explained by classical physics alone. It arises because quantum fluctuations in the vacuum behave differently in the space between the plates than in the space outside. This difference produces a measurable effect, showing that the vacuum is not empty, but filled with energy and activity. Another important idea related to this topic is the concept of quantum fields. In modern physics, particles are understood as excitations of underlying fields that exist throughout all of space. For example, there is a field associated with electrons, another with photons, and many more. These fields are always present, even in the vacuum. What we call a particle is simply a small disturbance or vibration in one of these fields. This means that even when there are no particles present, the fields still exist. They never switch off or disappear. Instead, they remain in their lowest energy state, known as the ground state. However, even in this minimum state, they are not completely at rest. They continue to fluctuate due to the uncertainty principle. These fluctuations are what give rise to virtual particles and other effects. The idea of fields filling all of space fundamentally changes the meaning of nothing. Rather than being a total absence, empty space becomes a background full of potential activity. The fields are always there and can produce particles when enough energy is added to them. This is observed in high-energy experiments, where particles are created from energy in particle accelerators. The presence of energy in empty space also has implications for the large-scale structure of the universe. One concept that arises from this is vacuum energy, the energy associated with empty space itself. This energy is believed to play a role in the expansion of the universe. Observations show that the universe is expanding at an ever-increasing rate, and one explanation for this involves a form of energy that exists even in empty space. This idea is closely related to what is known as dark energy. Dark energy is a term used to describe the unknown force that is causing the accelerating expansion of the universe. Although its exact nature is not fully understood, it may be connected to the vacuum energy predicted by quantum mechanics. This suggests that the activity within what appears to be empty space can influence the behavior of the universe at the largest scales. Quantum mechanics also shows that the vacuum can interact with matter in subtle ways. For example, the presence of virtual particles can slightly modify the properties of real particles, such as their mass or charge. These effects are small but measurable and have been confirmed through high-precision experiments. Another area where the active nature of the vacuum becomes important is the study of black holes. Near the boundary of a black hole, known as the event horizon, quantum effects can give rise to the production of particles. This process is associated with what is known as Hawking radiation, named after Stephen Hawking. According to this idea, black holes are not completely black, but can emit radiation due to quantum effects at their edges. In this process, pairs of virtual particles that form near the event horizon can become separated. One particle may fall into the black hole, while the other escapes into space. The escaping particle becomes real and can be detected as radiation. This once again shows that what appears to be empty space can give rise to real and observable effects. This shift in understanding has also changed the way scientists think about the origin of the universe. Some theories suggest that the universe itself may have originated from a quantum fluctuation in a vacuum. Although this idea is still being investigated, it shows how the concept of nothing has evolved in modern physics. In everyday life, the idea of empty space remains useful and practical. However, at the deepest level studied by physics, empty space is far from empty. It is a dynamic and active part of the universe, shaped by the laws of quantum mechanics and filled with processes that continue without pause. Quantum fluctuations are one of the most fascinating ideas in modern physics, and they challenge the simple belief that empty space is truly empty. When people first learn about space, they often imagine it as a vast region filled with absolutely nothing, a silent and inactive background where stars and galaxies exist. However, deeper scientific study has shown that this view is incomplete. Even in places where there are no atoms, no light, and no visible matter, space is not still. Instead, it is active in ways that are extremely small, extremely fast, and generally impossible to observe directly. These tiny activities are known as quantum fluctuations, and they reveal that space itself has a kind of restless behavior at the smallest levels. To understand this idea more clearly, it is useful to begin with how physics describes reality at very small scales. In everyday life, objects seem stable and predictable. A table stays in one place, a ball rolls across the floor, and a glass of water remains in its container unless something disturbs it. These experiences come from what scientists call classical physics, which works very well for large objects and ordinary situations. But when scientists began to study atoms and particles much smaller than atoms, they discovered that the rules change. This new set of rules is known as quantum mechanics, and it describes a world where certainty is replaced by probabilities, and where things do not behave in simple and predictable ways. One of the key ideas of quantum mechanics is that it is impossible to know everything about a system at the same time, with complete precision. This idea is often expressed through what is called the uncertainty principle. This states that certain pairs of properties, such as position and momentum, cannot both be measured exactly at the same instant. The more precisely one is known, the less precisely the other can be known. This is not due to a limitation of measuring instruments, but to a fundamental property of nature itself. This uncertainty plays a central role in the existence of quantum fluctuations. Because of this uncertainty, the energy in a small region of space cannot remain perfectly constant at all times. Even in what is considered empty space, there is a limit to how still energy can be. As a result, energy can briefly appear and disappear in very small amounts. These temporary changes in energy are what scientists call quantum fluctuations. They are not large bursts that can be seen or felt in everyday life, but extremely small and very short-lived events that occur everywhere, all the time. To describe this in a more detailed way, imagine a region of space that contains no particles. According to classical thinking, this region would have zero energy. However, quantum mechanics tells us that this is not possible. Instead, there is always a minimum level of energy present, known as vacuum energy. This energy does not come from particles or radiation, but from the underlying structure of space itself. Because of this, even the most empty space possible is filled with small temporary changes in energy. These changes can lead to the brief creation of pairs of particles. In quantum field theory, which is an extension of quantum mechanics, particles are understood as excitations of underlying fields. Each type of particle is associated with a field that exists throughout all of space. When energy fluctuates in a small region, it can create a pair of particles, such as an electron and its corresponding antiparticle called a positron. These particles appear together, exist for a very short time, and then disappear again. This process happens so quickly that it does not violate the conservation of energy, because the energy is returned to the vacuum almost immediately. The lifespan of these particle pairs is extremely short, far briefer than anything that can be observed directly with current technology. They are often referred to as virtual particles, because they cannot be detected in the same way as real particles that exist for longer periods. Despite this, their effects can still be measured indirectly. For example, they can influence the behavior of real particles, slightly modifying their properties in ways that can be detected in experiments. One important example of this influence is observed in the behavior of electrons. When an electron moves through space, it is not completely isolated. It interacts with the surrounding quantum fluctuations, including the temporary appearance of virtual particles. These interactions slightly alter the energy and movement of the electron. Scientists have measured these changes with very high precision, and the results match very closely with the predictions of quantum theory. This provides strong evidence that quantum fluctuations are real and have measurable effects. Another example can be found in a phenomenon known as the Casimir effect. This occurs when two very flat surfaces are placed very close to one another in a vacuum. According to quantum theory, the space between the surfaces allows fewer quantum fluctuations than the space outside. This difference creates a small force that pushes the surfaces toward each other. This force has been measured in laboratory experiments, providing additional confirmation that empty space is not truly empty, but filled with fluctuating energy. Quantum fluctuations are also believed to play an important role in the early history of the universe. In the first stages following the beginning of the universe, conditions were extremely hot and dense. During this time, small fluctuations in energy may have been stretched to larger scales as the universe expanded. These small variations could have given rise to the formation of galaxies and other large structures that we see today. In this way, the smallest possible changes in energy may have had a lasting impact on the largest structures in the universe. The idea that space can produce and destroy energy at small scales may seem unusual, but it follows directly from the rules of quantum mechanics. These rules have been tested in many experiments and have consistently provided accurate predictions. Although the effects of quantum fluctuations are usually very small, they are always present and form a fundamental part of how the universe works at its tiniest levels. It is also important to understand that these fluctuations do not mean that energy is being created from nothing in a way that violates physical laws. The changes in energy are temporary and are limited by the uncertainty principle. Over longer periods, the average energy remains constant. This ensures that the overall balance of energy is conserved, even though small changes occur constantly at very short timescales. One area of interest is the relationship between quantum fluctuations and gravity. Gravity is described by a different theory, known as general relativity, which works very well for large objects such as planets and stars. However, combining general relativity with quantum mechanics has proven to be very difficult. Understanding how quantum fluctuations behave in the presence of strong gravitational fields may provide important clues for developing a unified theory that describes all fundamental forces. Another area of research involves the role of quantum fluctuations in black holes. Near the boundary of a black hole, known as the event horizon, quantum effects become very important. Some theories suggest that quantum fluctuations near the event horizon can give rise to the emission of radiation, a process known as Hawking radiation. This radiation would cause black holes to lose energy over time. Although this effect is very difficult to observe directly, it is a key prediction that connects quantum mechanics with gravitational physics. Quantum fluctuations also raise questions about the nature of the vacuum itself. If empty space contains energy and activity, then it may have properties that can be studied and understood in greater detail. Some theories suggest that the vacuum could have different states, each with different levels of energy. Transitions between these states could have significant effects on the structure of the universe. In addition to their importance in physics, quantum fluctuations have influenced the way scientists think about reality at a fundamental level. They show that what appears empty and inactive may in fact be filled with hidden processes. This challenges simple ideas about space and encourages a deeper exploration of how the universe works at its most basic level. The concept of constant activity in empty space also connects with the idea that fields exist everywhere, even in regions without particles. These fields are never completely at rest, and their small movements and changes give rise to quantum fluctuations. This means that the vacuum is not just a passive background but an active part of the physical world. Although quantum fluctuations are extremely small, their presence is constant and inevitable. They are a natural result of the principles of quantum mechanics and play a role in many different physical processes. From influencing the behavior of particles to contributing to the formation of cosmic structures, these tiny bursts of activity are an essential part of the universe. As knowledge in this field continues to grow, understanding quantum fluctuations may lead to new technologies and applications. Although many of these possibilities are still theoretical, the study of quantum mechanics has already given rise to important developments, such as semiconductors, lasers, and quantum computing. New insights into the behavior of energy at the smallest scales could open the door to even greater advances in the future. The idea that space constantly produces and destroys energy at the smallest scales is not just a theoretical concept, but a well-supported part of modern physics. It reflects the complex and dynamic nature of the universe, even in places that appear completely empty. By continuing to explore these ideas, scientists are gradually building a more complete picture of reality. one that includes both the visible and hidden aspects of the physical world. The idea of virtual particles begins with a deep examination of how modern physics understands space, energy, and existence at the smallest possible scales. In everyday thinking, people tend to imagine empty space as something that contains absolutely nothing, a silent and motionless background where objects simply exist and move. However, when scientists study space using the rules of quantum physics, they discover that what appears empty is actually filled with constant activity. This activity is not always visible or easily measurable in a direct way, but it plays a very important role in how the universe behaves. Within this activity, virtual particles appear as very short-lived events that exist for an extremely brief instant before disappearing again. Virtual particles are not particles in the usual sense that people think of when they imagine things like electrons or protons. Those familiar particles can be detected, measured, and tracked over time. They have clear properties such as mass, charge, and position. Virtual particles, on the other hand, exist in a more subtle and fleeting way. They are described through the mathematical rules of quantum field theory, a framework that explains how fields and particles interact at very small scales. In this framework, each type of particle is linked to a field that fills all of space. These fields are always present, even when there are no visible particles around. Within these fields, small disturbances can occur. These disturbances can briefly behave like particles, although they do not behave like stable and lasting objects. This is what scientists call virtual particles. They are permitted to exist due to a principle of quantum physics, known as the uncertainty principle. This principle states that certain pairs of physical properties, such as energy and time, cannot both be known with perfect precision at the same time. Because of this uncertainty, the laws of physics allow small amounts of energy to appear for a very brief time, as long as that energy disappears again quickly enough. This temporary energy can give rise to virtual particles. They are created from the fluctuations of the fields that fill space. These fluctuations occur constantly, even in what appears to be a complete vacuum. As a result, virtual particles can appear and disappear on a continuous basis, forming a kind of hidden activity that underlies everything in the universe. Their existence is not observed directly in the same way as ordinary particles, but their effects can be measured in experiments. One of the most important aspects of virtual particles is how they influence interactions between real particles. For example, when two charged particles interact with each other, such as two electrons, the force between them can be explained as if it were carried by virtual particles. These virtual particles act as messengers that transfer energy and momentum between the real particles. Although the virtual particles themselves cannot be detected directly, their presence is necessary to explain how the interaction takes place. In quantum field theory, forces are understood as being mediated by these virtual particles. The electromagnetic force, which is responsible for the behavior of charged particles, is carried by virtual photons. These photons are not the same as the particles of light that can be detected by the human eye or by instruments. Instead, they are temporary disturbances that exist only during the interaction. They appear, transfer energy, and then disappear, all within an extremely short time. The concept of virtual particles also plays a role in explaining the structure of atoms and the behavior of subatomic particles. Inside an atom, electrons move in regions described by probabilities rather than fixed paths. The forces that hold the atom together involve the exchange of virtual particles. These exchanges occur constantly, creating a dynamic environment even within something that appears stable. Another important area in which virtual particles are involved is the behavior of the vacuum. In classical physics, a vacuum is defined as a space without matter. In quantum physics, the vacuum is not truly empty. It is the lowest energy state of a field, but it still contains fluctuations. These fluctuations can produce pairs of virtual particles, such as a particle and its corresponding antiparticle. These pairs appear together and then quickly cancel each other out, returning the energy to the vacuum. The idea of particle and antiparticle pairs is fundamental to understanding virtual particles. Every type of particle has a corresponding antiparticle with opposite properties, such as charge. When a virtual pair is created, the particle and the antiparticle exist briefly before annihilating each other. This process happens so quickly that it cannot be observed directly, but it contributes to the overall behavior of quantum fields. One of the ways in which scientists have found evidence of virtual particles is through precise measurements of physical effects. For example, there is an effect known as the Casimir effect, in which two metal plates, placed very close together in a vacuum, experience a small force pushing them toward each other. This force can be explained by the behavior of virtual particles in the space between the plates. The presence of the plates changes the way quantum fields fluctuate, giving rise to a measurable effect. Another example is the small shift in the energy levels of electrons in atoms, known as the Lamb shift. This shift occurs because the electron interacts with virtual particles in the vacuum, which slightly alters its energy. This effect has been measured with great precision and matches the predictions made by quantum theory. Virtual particles also play a role in processes involving high-energy physics. In particle accelerators, where particles collide at very high speeds, virtual particles can appear as intermediate steps in reactions. When two particles collide, the energy of the collision can briefly create virtual particles, which then transform into other particles that can be detected. These processes are described using diagrams that show how particles interact through the exchange of virtual particles. These diagrams, often called Feynman diagrams, provide a way to visualize complex interactions. In these diagrams, virtual particles are represented as lines connecting different points. They show how energy and momentum flow during an interaction. Although the virtual particles themselves are not observed directly, the diagrams help scientists calculate the probabilities of different outcomes. The idea of virtual particles challenges the traditional view of what it means for something to exist. In everyday life, objects are expected to have a clear presence, to persist over time, and to be observable directly. Virtual particles do not fit this description. They exist only within the limits allowed by quantum uncertainty, and they do not have a stable and independent existence. Their role is more related to facilitating interactions and contributing to the behavior of fields. This raises questions about the nature of reality at very small scales. If particles can appear and disappear in such a brief and indirect way, it suggests that the foundation of the universe is not made up of solid and unchanging pieces. Instead, it is based on processes and interactions that are occurring constantly. The fields that fill space are always active, and virtual particles are one of the ways in which this activity becomes apparent. The mathematics used to describe virtual particles are complex and involve advanced concepts from quantum theory. These mathematical descriptions allow scientists to make very precise predictions about experimental results. Although the idea of particles appearing from nothing may seem unusual, the predictions made using this concept have been confirmed many times through experiments. It is important to understand that virtual particles are not created from absolute nothing. They arise from the energy present in quantum fields. The term "from nothing" reflects the fact that they do not come from a specific location or source in the usual sense. Instead, they are a natural consequence of the way quantum fields behave. The presence of virtual particles also affects the properties of empty space. For example, the vacuum can have associated energy due to these fluctuations. This vacuum energy is an important concept in cosmology, the study of the universe as a whole. It is related to ideas about dark energy and the expansion of the universe, although the exact connections are still being investigated. Virtual particles also participate in processes near very strong gravitational fields, such as those surrounding black holes. In these extreme environments, the effects of quantum fields become significant. Some theories suggest that virtual particle pairs near the boundary of a black hole can give rise to the emission of radiation, a process known as Hawking radiation. In this process, one particle from the pair falls into the black hole, while the other escapes, making it appear as though the black hole is emitting particles. This idea shows how virtual particles can have observable consequences even under extreme conditions. It also highlights the connection between quantum physics and gravity, two areas of physics that are still being brought together into a unified understanding. As experiments become more precise and new technologies are developed, it may become possible to explore the effects of virtual particles in greater detail. This could lead to new insights into the nature of space, time, and energy. The concept of virtual particles already plays a central role in modern physics and continues to influence the way scientists understand the universe at its most fundamental level. The idea that particles can appear and disappear so quickly challenges simple intuitions, but also provides a powerful tool for understanding complex interactions. By accepting the principles of quantum theory, scientists can use the concept of virtual particles to explain a wide range of phenomena, from the behavior of atoms to the forces that govern the universe. The presence of these brief and subtle events suggests that what is often considered empty space is far more active than it appears. Every point in space is part of a network of fields that are constantly fluctuating. Virtual particles are an expression of this activity, showing that even in the absence of visible matter, a rich and dynamic structure still exists at the smallest scales. This continuous activity never stops or settles into stillness. It goes on at all times, driven by the fundamental rules of quantum physics. The appearance and disappearance of virtual particles is one of the many ways in which this activity makes itself known. Dark energy is a term used by scientists to describe a form of energy that is believed to exist throughout all of space. It is not something that can be seen, touched, or measured directly in a simple way, and yet it plays a very important role in shaping the universe. The idea of dark energy comes from careful observations about how the universe behaves at the largest scales. Over time, scientists discovered that the universe is not only expanding, but that this expansion is accelerating. This result was surprising, because earlier expectations suggested that gravity should be slowing the expansion down. To understand dark energy, it is useful to begin with the idea of space itself. Space is often described as empty, but in modern physics, it is not truly empty. Even in regions far from stars and galaxies, space still has properties and can contain energy. This energy is not like the energy of light or heat. Instead, it is a form of energy that is distributed uniformly throughout space and does not clump together. This is one of the key characteristics that makes dark energy different from matter and radiation. The story of dark energy began to take shape when astronomers started studying distant exploding stars, known as supernovas. These events are extremely bright and can be seen from very far away. Because their brightness follows a known pattern, they can be used to measure distances in space. By comparing how bright these supernovas appear with how bright they are expected to be, scientists can estimate how far away they are. At the same time, by studying the light from these supernovas, scientists can determine how fast they are moving away from us. When researchers carefully measured many of these distant supernovas, they noticed something unexpected. The supernovas were dimmer than expected, which meant they were farther away than previous models had predicted. This suggested that the universe had expanded more than expected during the time the light was traveling, the conclusion was that the expansion of the universe is accelerating rather than slowing down. This discovery led scientists to propose the existence of dark energy as a way of explaining this acceleration. Dark energy is believed to make up the largest portion of the total energy content of the universe. Ordinary matter, which includes everything that can be seen, such as stars, planets, and galaxies, accounts for only a small part. There is also dark matter, another invisible component that affects gravity but does not emit light. However, dark energy is even more dominant. It is considered to represent the vast majority of the total energy of the universe. One of the simplest ways in which scientists describe dark energy is through the idea of a constant energy density that fills space. This means that as space expands, more space appears, and with it, more dark energy appears as well. This does not violate known physical laws because the energy is associated with space itself. In this view, dark energy has a constant density, so as the volume of the universe increases, the total amount of dark energy also increases. This idea is closely related to a concept introduced earlier in the history of physics called the cosmological constant. This concept was originally proposed as part of the equations that describe gravity and the structure of the universe. At the time, it was introduced for a different reason, but it later became useful again as a way of describing dark energy. In this framework, dark energy is treated as a property of space that produces a repulsive effect, leading to accelerated expansion. The effect of dark energy can be understood in terms of how it influences the movement of galaxies. In the absence of dark energy, the gravity of matter would act to slow the expansion of the universe. Over long periods of time, this could even lead to a collapse. However, with dark energy present, there is an additional effect acting in the opposite direction. This effect causes space itself to expand more rapidly, pushing galaxies farther apart from one another over time. This expansion does not mean that galaxies are moving through space in the usual sense. Instead, it is the space between galaxies that is stretching. As space expands, the distance between objects increases. This effect becomes more noticeable at very large distances. At smaller scales, such as within galaxies or solar systems, gravity is strong enough to hold structures together, so the expansion does not pull them apart. The presence of dark energy also affects the overall shape and fate of the universe. Scientists use observations of the cosmic microwave background, the distribution of galaxies, and the brightness of distant supernovas to estimate the amount of dark energy. These observations suggest that the universe is very close to being flat in terms of its geometry, and that dark energy plays a key role in maintaining this balance. Another important aspect of dark energy is its pressure. In physics, pressure is not something that applies only to gases and liquids. It can also be used to describe how energy behaves in space. Dark energy is thought to have a type of negative pressure. This negative pressure is what drives the accelerated expansion. It works in a way that causes space to expand rather than contract. The exact nature of dark energy is still unknown. Several theories attempt to explain it. One possibility is that it is simply the energy of empty space, as described by the cosmological constant. Another possibility is that it is a dynamic field that changes over time. This type of field is sometimes called quintessence. In this model, dark energy is not constant, but evolves as the universe expands. Scientists also consider other explanations that involve modifications to the laws of gravity. In these theories, the observed acceleration is not due to a new form of energy, but to a change in the way gravity behaves at very large scales. These ideas are still being tested and require careful comparison with observations. To study dark energy, scientists use a wide range of tools and methods. Telescopes that observe distant galaxies and supernovas provide important data about how the universe has expanded over time. Measurements of the cosmic microwave background provide information about the early universe and help establish the initial conditions of the expansion. Studies of the distribution of galaxies reveal patterns that are influenced by the presence of dark energy. Large observational projects are designed to improve our understanding of dark energy. These projects aim to map the positions and movements of millions of galaxies, measure the brightness of distant supernovas, and study the structure of the universe in detail. By combining these different types of observations, scientists can establish more precise limits on the properties of dark energy and test different models. The study of dark energy also connects with quantum physics. In quantum theory, even empty space is not completely empty. It contains fluctuations and virtual particles that appear and disappear in very short times. These fluctuations contribute to the energy of space. However, when scientists attempt to calculate this energy using quantum theory, the result is much larger than the observed value of dark energy. This difference is one of the greatest unsolved problems in physics. Another area of research involves understanding how dark energy interacts with other components of the universe. For example, scientists investigate whether dark energy affects the growth of cosmic structures, such as galaxies and clusters. They also study whether the properties of dark energy change over time or remain constant. The idea of dark energy has changed the way scientists think about the universe. Before its discovery, the focus was mainly on matter and gravity. It is now clear that a large part of the universe is made up of something that is not directly visible and that behaves in a very different way. This has given rise to new questions about the fundamental nature of reality and the laws that govern it. One of the main challenges in studying dark energy is that it does not interact strongly with other forms of matter. This makes it difficult to detect directly. Instead, its presence is inferred from its effects on the expansion of the universe. The expansion of the universe can be described using mathematical models that take into account different components such as matter, radiation, and dark energy. These models are based on equations that relate the rate of expansion to the energy content of the universe. By comparing these models with observations, scientists can determine which combination of components best fits the data. As the universe continues to expand, the influence of dark energy becomes more dominant. In earlier times, when the universe was smaller and denser, matter played a greater role in determining the rate of expansion. Over time, as the universe grew, the effect of dark energy became more significant. This transition marks an important stage in the history of the universe. The long-term behavior of the universe depends on the properties of dark energy. If dark energy remains constant, the universe will continue to expand at an accelerating rate. If it changes over time, the future could be different. Some models suggest that the expansion could slow down or even reverse, while others indicate that it could become even faster. Dark matter and the idea of emptiness are closely related in a way that has changed how scientists understand the universe. For a long time, it was believed that empty space was truly empty. It was considered a place where nothing existed, where there were no particles, no energy, and no structure. Over time, careful observation and deeper study began to question that idea. Scientists started to notice that something invisible seemed to be present, something that could not be observed directly, but that still had clear effects on the world around it. This invisible presence is now called dark matter, and it plays an important role in the way the universe behaves. When people look at the night sky, they see stars, planets, and sometimes faint clouds of gas and dust. These visible objects represent only a small part of the universe. For many years, scientists assumed that most of the mass of the universe came from these visible objects. However, when they began to measure how galaxies move, they found something unexpected. The stars within galaxies were moving in a way that could not be explained by visible matter alone. The outer parts of galaxies were rotating much faster than expected. According to the known laws of motion and gravity, those outer stars should have moved more slowly. or even scattered into space. But they did not. They remained in place, firmly held within their galaxies. This strange behavior led scientists to think that there must be more matter than could be seen. This hidden matter did not emit light, did not reflect it, and did not absorb it in a way that could be easily detected. It appeared completely invisible. Although it could not be seen, its presence could be felt through its gravitational pull. This was the beginning of the idea of dark matter. Dark matter is not something that can be observed directly with telescopes. It does not shine like stars, nor does it block light in a way that produces shadows, as dust clouds do. Instead, it reveals itself through its influence on the movement of objects. When scientists measure how galaxies rotate, how clusters of galaxies hold together, and how light bends as it passes through space, they find clear signs that large amounts of invisible mass are present. This invisible mass is what is called dark matter. The idea that empty space might not truly be empty becomes clearer when dark matter is considered. What appears to be empty space may actually contain large amounts of this invisible material. Although it cannot be seen, it is still there, affecting everything around it. This challenges the simple idea that emptiness means the absence of everything. Instead, emptiness may mean only the absence of things that can be easily detected by human senses or simple instruments. The study of galaxies provided some of the earliest and strongest evidence of dark matter. When scientists measured the speed of stars at different distances from the center of a galaxy, they expected to observe a decrease in speed as the distance increased. This expectation was based on the understanding of gravity and how it acts on visible matter. However, observations showed that the speeds remained high, even far from the center. This suggested that more mass was present than could be explained by the visible stars and gas. This hidden mass had to be distributed throughout the galaxy, forming a kind of invisible structure around it. This structure is often described as a dark matter halo. The galaxy sits within this halo, and the gravity of the dark matter helps hold it together. Without this additional mass, the galaxy would not be stable in the way that is observed. The idea of dark matter also helps explain how galaxies formed in the first place. In the early universe, matter was distributed more uniformly. Over time, small differences in density grew under the influence of gravity. Regions with a little more matter began to attract more material, becoming larger and denser. Dark matter played an important role in this process because it provided additional gravitational pull. It helped gather matter more quickly, allowing galaxies to form earlier than would otherwise have been possible. Although dark matter does not interact with light, scientists believe it interacts with gravity in the same way as ordinary matter. This means it contributes to the overall gravitational field of the universe. It helps shape the large-scale structure of the cosmos, influencing how galaxies are distributed and how they move relative to one another. Another important piece of evidence for dark matter comes from the study of galaxy clusters. These clusters are large groups of galaxies that are held together by gravity. When scientists calculate the total mass of a cluster based on the movement of the galaxies within it, they find that visible matter accounts for only a small fraction of the total mass needed to hold the cluster together. The rest must be made up of dark matter. In addition to affecting the movement of galaxies, dark matter also influences the way light travels through space. According to the theory of gravity, mass can bend the path of light. This effect is known as gravitational lensing. When light from a distant object passes near a massive object, its path is bent. This can make the distant object appear distorted or even create multiple images of the same object. By studying gravitational lensing, scientists can map the distribution of mass in the universe, including dark matter. They can see where mass must be located based on how light is bent. These studies show that large amounts of mass exist in places where there is no visible matter. This provides strong evidence that dark matter is real and that it is distributed throughout the universe. The idea that empty space could be filled with invisible matter changes the way people think about the nature of reality. It suggests that what is visible is only a small part of what exists. Much of the universe may be hidden from direct observation, and yet still have a powerful influence on everything that can be seen. Scientists have proposed different ideas about what dark matter could be made of. Some think it could consist of new types of particles that have not yet been detected. These particles would not interact with light, making them invisible, but they would still have mass and exert gravitational force. Experiments are being carried out to try to detect these particles, but so far no direct detection has been confirmed. Other ideas suggest that dark matter could be made up of objects that are difficult to see, such as very faint stars or small black holes. However, studies have shown that these objects cannot account for all of the missing mass. This has led scientists to focus more on the idea of new types of particles. The search for dark matter is one of the most active areas of research in modern science. Scientists use large detectors placed deep underground to try to observe rare interactions between dark matter particles and ordinary matter. They also use powerful accelerators to try to create these particles in controlled experiments. In addition, telescopes are used to search for indirect signals of dark matter, such as signals that might be produced when dark matter particles interact with one another. Although dark matter has not yet been directly observed, the evidence for its existence is strong. The way galaxies move, the way galaxy clusters hold together, and the way light bends all point to the presence of invisible mass. This has led most scientists to accept that dark matter is a real and important part of the universe. The idea of emptiness becomes more complex when dark matter is taken into account. What appears to be empty space may actually be filled with this invisible substance. This means that the void is not simply the absence of matter, but rather a state in which matter may be present in forms that are not easy to detect. Dark matter also plays a role in the overall balance of the universe. When scientists study the large-scale structure of the cosmos, they find that dark matter makes up a significant portion of the total mass. This means it has an important influence on how the universe evolves over time. The presence of dark matter affects the way galaxies interact with one another. When galaxies pass close to each other, their movement is influenced not only by the visible matter they contain, but also by their dark matter halos. This can affect the way galaxies merge and how their structures change over time. The idea that invisible matter exists in what appears to be empty space challenges simple definitions of nothing. It shows that the universe is far richer and more complex than what can be seen with the naked eye, or even with powerful telescopes. What appears to be a vast and empty void may in fact be filled with material that plays a crucial role in shaping the cosmos. This understanding continues to grow as scientists develop new tools and methods to explore the hidden aspects of the universe, pushing the boundaries of what is known and opening new questions about the true nature of space, matter, and existence itself.